the eigenvalue and the eigenvector. The eigenvalue lambda and the eigenvector v. Note, the differential equation dx dt equals ax, where a is a constant, has the general solution x of t equals c times e to the at. What this right here says that the derivative of x with respect to t is the same as the original x multiplied by the constant a. This x, when it acts this way with its differential, it's of this nature, c times e to the power at. Let's take a look. So if I take x as c times e to the power at and I multiply by d dt to find its differential, a on the exponent will go up front, as you could see, and this right here boxed is the same thing right here, which means the differential of x with respect to t is the same as x multiplied by a constant. This happens when your functions x are of this look right here, exponential functions with base e. Next, when we have a system as dx1 dt equals a11 x1 plus a12 x2, and dx2 dt equals a21 x1 plus a22 x2. It will have the general solution x of t equals e to the lambda t times v, where v is a vector of the components v1 and v2. x1 and x2, these x1 and x2 are functions of independent variable t, and aij are the constants, the coefficient matrix. So this system could be looked at as earlier this way. This is a coefficient matrix, that's a variable matrix, that's a differential matrix, and this whole thing could be written as dx dt equals a, this a multiplied by this x. So dx dt equals a times x of t. d dt of x, and x is e to the lambda t v right here, will be a multiplied by x, that's a, and that's my x right there. Derivative of this will be lambda will go up front, and we'll have the following: lambda times e to the lambda t v equals a times e to the lambda t v. If I take e to the lambda t out from both sides, I will get av equals lambda v. So if you write this the other way around, we will have the following: av equals lambda v. Next, so av equals lambda v, replacing v with iv, any matrix v times I or the identity matrix will not change anything. So V equals IV. Moving everything to the left, I'll have AV minus lambda IV equals 0. Taking V out as a common factor from the right hand side, so focusing on V as a common factor, we will have A minus lambda I times V equals 0. This right here will have a non-trivial solution if and only if the determinant of A minus lambda I equals 0. From a previous section we had the following: a homogeneous system, linear system, that is written as AX equals 0, number 1, has the trivial solution x equals 0 if and only if determinant of A does not equal to 0. Has an infinite number of solutions if and only if determinant of A equals 0. Now, we know that the determinant of A does not equal to 0 means it is invertible. So A inverse exists. The first one is so simple, because if you have AX equals 0 and the determinant does not equal to 0, which means A inverse exists. So multiplying the left by A inverse, multiplying here by A inverse times 0 is 0. A inverse times A will change to I, and I times X is X. That will give you X equals 0, called the trivial solution. So in order to have the non-trivial solution, we need the determinant of A to be 0. Next, focusing on A minus lambda I V equals 0, this will have the non-trivial solution if and only if the determinant equals 0 of A minus lambda I. Let's go back to the eigenvalue and eigenvector idea. Verify that V equals 1, 3 is an eigenvector of the matrix A equals 1, 1, negative 3, 5, corresponding to the eigenvalue lambda equals 4. This is just like a very simple example just to give you a connection between the title lambda and V. The title of this section is the eigenvalue lambda and the eigenvector V. Every lambda will correspond to vectors V, and every vectors will correspond to lambda. So they kind of like go together. You'll see more about what I mean by lambdas and V's in the coming examples. This is just an introduction example. So we have A times V. Our A is given, our V is given, so let's write them down. So we have 1, 1, negative 3, 1 for A, and for V I have 1, 3 right there. To multiply 2 by 2 times 2 by 1, we get 2 by 1, and that's a 4 and 12. If I factor 4 out from this matrix, I will have 4 times the matrix 1 and 3. But what's 1, 3? 1, 3 is our vector V, and what's 4? Our lambda 4. So as they say, verify that V equals 1, 3 is an eigenvector, that's this right here, of the matrix A, that's this right here, corresponding to the lambda equals 4. So AV equals lambda V. It's kind of saying that you multiply a matrix A by V, it's the same thing as multiplying the number lambda times V. Just to give you an idea how lambda and V communicate and correspond to each other this way. Now, we say V is an eigenvector of A corresponding to the eigenvalue lambda equals 4. Example: find all eigenvalues and eigenvectors of A equals 3, -1, -5, -1. This is the first example that we take, so I'm gonna slow down and show all the steps. You'll be skipping those beginning steps in the coming examples. So we have A minus lambda I times V equals 0. A right here minus lambda times I, and I is 1, 0, 0, 1, the identity matrix, times V has the components small v1 and small v2, equals 0, which is a matrix of size 2 by 1, 0, 0. Multiplying lambda inside here, that will look like lambda 0, 0, lambda. Then we're going to subtract those two matrices. Lambda is inside. Subtracting these two, the first element will be 3 minus lambda. The second element will not change, -1 minus 0, and so on. So I have the following. As we talked earlier, this will have the non-trivial solution if the determinant of this matrix, which is A minus lambda I, is equal to 0. The system has non-trivial solutions if and only if the determinant of this is equal to 0. We multiply and we go back and subtract the multiplication of -5 and -1, and that's like minus a positive 5. Now, skipping the algebra steps right here, using the distributive, combining the constants, and factor back again, we end up with lambda squared minus 2 lambda minus 8 equals 0, which factors to lambda plus 2 times lambda minus 4 equals 0. So I have two lambdas. It says right here, find all eigenvalues and eigenvectors of A equals 3, -1, -5, and 1. We found two lambdas. So we're going to take our time step by step for each lambda. This is our first example. These steps right here, you could skip them later on or make it faster. Instead of writing the whole thing, you could just go 3 minus lambda, minus 1 minus lambda, and find the determinant of that matrix by converting 3 and -1 to 3 minus lambda and -1 minus lambda, which is right here. So these steps will be skipped if you like to. It's totally fine. Just jump to this determinant and do the algebra steps right here. Let's go after lambda 1. If you call it lambda 1, it doesn't matter which one is lambda 1. Equals -2, and we'll move on. So we have two lambdas. Here's the first lambda. Lambda 1 equals -2. So we go back, and right here we write 3 minus lambda 1, and here we write -1 minus lambda 1, but lambda 1 is -2. So 3 minus -2, and that will be 3 minus -2 times 1, that's the full steps, which is 5. So 3 minus -2 is 5. -1 minus -2 will be -1 plus 2, which is 1. Notice this column, or I mean this diagonal, does not change. It's -1 and -5. Lambdas only affect this main diagonal. So Now we're looking at the system to solve, which is a minus lambda I times v equals 0. In short, we write it this way as an augmented matrix. Now, notice that -5 is the opposite of 5 and 1 is the opposite of -1. So if you want to cancel, you multiply this by 1 and go down, everything cancels. So the second row becomes zeros. Now you want the 5 to be 1, you divide by 5, and this -1 becomes -1 over 5. Now usually we go backwards and we have a free variable, so we call x2 equals t, but this time I'm going to call x1 equals t. You'll see why. You don't have to, but that's an option. To show the steps, x1 plus -1/5 x2 equals 0. And as I said, I'm going to call x1 equals r, not x2. Usually, as I said, the book says go backwards or back substitution. We're going to take x1 as a free variable. Why is that? Think of this one as being r. Multiply both sides by 5. You don't see the fraction 1/5 anymore. So this right here will look like 5x1 equals x2. So if you know x1, to find x2 you multiply by 5. So if x1 equals r, x2 equals 5r. The solution becomes v is r that we called for x1, and x2 is 5r, where r is a free variable. Factor r out to see the clear vector that sometimes we refer to as the basis. It's 1 and 5. The eigenvector corresponding to the eigenvalue lambda 1 equals -2 is v1 equals 1 and 5. So because we call this one lambda 1, we're calling the solution v1. Let's go to the lambda 2. Lambda 2 is 4. We do the same process. We plug in our system, instead of lambda 2, 4, and we subtract 5 minus was it 5? It's 3. 3 is up front. So we have 3 minus 4 will give you a -1. Skipping the steps, as you can see, just like the first one. Also, I'm skipping the steps to reduce right here. So if you want to cancel, you see it's duplicates, right away it cancels. Then divide or multiply by -1, you get 1, 1, 0, 0, 0, 0. Not too hard to write the solution set for it, but I could see that x2 is up and x1 adds up to 0, which means moving x2 on the other side or x1 on the other side, they're opposites. So if s is a free variable for x2, minus s will be the output for x1. So v2 that corresponds to lambda 2 is -1, 1, -1, 1. Note, A is called non-defective. Why is that? If you remember the matrix A, it was a 2 by 2. So we call n equals 2. Since we have n equals 2, we should expect or look for two vectors. We found v1 and v2. This is v2. So by having v2 equals -1, 1, and v1, what was it? V1 was 1 and 5. So I have two vectors. Two vectors with n equals 2, that means non-defective. What do I mean by that? If n equals 3, we have a matrix of 3 by 3, that's for the coming section, and you end up with three vectors, v1 and v2 and v3, we call it non-defective. But if n equals 3 and you end up with only one vector, sometimes it happens, we don't have enough vectors. We need to look for or find 3 vectors to call it non-defective. So if you have less than 3, we call it defective. This one we have n equals 2 vectors. In short, we call it non-defective. Let's take another example. Find the eigenvalues and the eigenvectors of A equals 1, 1, 0, 1. Same process, more practice. The system A minus lambda I times V equals 0 has non-trivial solutions if and only if the determinant of A minus lambda I equals 0. So we have here 1 minus lambda, 1 and 0 stays the same, and we look for the determinant. 1 minus lambda times 1 minus lambda minus 0, or the other way, lambda minus I multiplied by itself twice. If you want to set this equal to 0, you get lambda equals 1, but we don't get 2 lambdas here, if you notice. So the first example was 2 distinct lambdas, 2 distinct vectors, 1 for each lambda. This example gives me 1 lambda that is repeated. So we have lambda 1 equals 1, we don't have lambda 2. We call it lambda 1 equals 1 repeated twice. So we go back and we plug in 1 in our system to solve this right here. So if lambda 1 equals 1, I get here 1 minus 1 and I get here 1 minus 1, I will have 0, 0 in the main diagonal. To solve this, we write it as augmented matrix. So you have 0, 1, 0 and 0, 0, 0. Now you have to be careful here. I'm gonna slow down and maybe use different colors to highlight and let you pay enough attention. I've seen students in other sections, when they solve this, they say V2 equals 0 and they stop right there, or they move on to something else, which is not true. Let me show you why. If you want to translate this, that's called 0v1 instead of calling it x1 and x2. The vector v is v1 v2, so I'm using v1 v2. 0v1 plus 1v2 equals 0. 0v1, it's just 0. So I have 1v2 equals 0, or in short, v2 equals 0. That is clear. v2 is 0, we all agree on. What about v1? Well, imagine if you put 5 here. If you put 5 here, that's still going to be true. 0 times 5 is 0. It's going to be away, gone. 0 times 7 is also true. We'll make this whole thing true. So one more time, you have to be careful here. We have 0 v1 equals 0. So v1 could be anything. Be careful. v1 is a free variable. One more time, if you don't pay enough attention to that, you're gonna make a mistake. I've seen it before with students. Just be careful. Whenever you see something like that, just slow down or pay attention to this right here, as a free variable is not a 0. So our solution. Now my handwriting v1 here looks like this v1, which is not true. My point is, this is the vector v1 that corresponds to this lambda 1, which has the components v1, v2. So it's kind of hard to write them with the font as like tilted small fonts right here for the components, but that's a vector and those are the components. Okay, so our vector, if you factor r out, we have r times 1, 0. So the basis is 1, 0, or the clean vector is 1, 0. I call it the clean vector. Now, since we do not have enough linearly independent vectors or eigenvectors, Since n equals 2, we don't have enough vectors, and we call the matrix A that was given to me with n equals 2 defective. Keep that in mind. So this theorem says it's good to know and keep in mind. Let A be an n by n matrix with real elements. If lambda is a complex eigenvalue of A with corresponding eigenvector V, then lambda conjugate, or the conjugate of lambda, is an eigenvalue of A, the same A, with a corresponding eigenvector V conjugate. The following example is going to help us see it in clear. We're going to use complex numbers, or we're going to end up with complex numbers. So what this says is, once you are dealing with complex eigenvalues, you know usually the solution for a second degree equation, if you have a second degree equation and you want to factor, one of the cases is you end up with imaginary numbers. So you end up with complex values, and they usually happen in conjugates. It's like 3 plus 2i and 3 minus 2i, 3 plus minus 2i. That's the idea right here. So if you find one, the other one will be its conjugate. Once you find the vector v that corresponds to this lambda, you don't have to worry about finding this vector v for lambda conjugate. For my example, 3 plus 2i, 3 minus 2i. So if you find the vector that corresponds to 3 plus 2i, this will be 3 minus 2i, and you don't have to look after the vector v that corresponds to 3 minus 2i. You just take this vector, apply the conjugate to it, and you're done. Here's a short proof for this. So we have AV equals lambda v, and apply the conjugate to both sides. We'll have the conjugate of AV equals the conjugate of lambda v, but A is real numbers. As you can see, the theorem says real numbers, real elements. So the conjugate, when you apply it to A, it doesn't make any difference. It stays A. Conjugate of V, conjugate of lambda, conjugate of V. Since A is just real elements. What this says is, this V is the vector that corresponds to this lambda. We already mentioned that lambda in complex numbers, they move on with conjugates. So lambda 1 will be, and lambda 2 will be conjugates. So if this V corresponds to this lambda, and this is the conjugate of this lambda, the V that corresponds to the conjugate of lambda will be the conjugate of the original vector. Let's take an example. Find all eigenvalues and eigenvectors of A equals 9, 37, negative 1, and negative 3. If we know how to start, we find the determinant of 9 minus lambda minus 3 minus lambda, and we'll move on. Once you simplify, skipping the algebra steps, looking for the determinant, this is a determinant, you get lambda squared minus 6 lambda plus 10 equals 0. You can't factor it with real numbers, so you end up with complex. So we have 3 plus I. That's going to be called lambda 1. Lambda 2 is going to be called 3 minus I. That's the conjugate of lambda 1. Okay, now let's take lambda 1 and work with it, and we'll come back to lambda 2. Lambda 1 equals 3 plus I. Taking 3 plus I up here, as the system A minus lambda I, this will be 9 minus 3 plus I, which is 9 minus 3 minus I. You do the same thing here and you leave this diagonal without any change. So one more time, let's double check. 9 minus this much, that's why you get the 6, minus I is right there. Okay, now to do the to simplify this with complex numbers, I'm gonna multiply this -1 by 6 minus I. I already have the negative sign. That's gonna make it the opposite of this to cancel it. Now I'm canceling this to make it 0, and then I'll take advantage of this -1 to have it on top as a leading coefficient 1. So here we go. What happens as you simplify, the first row all cancels. It's all zeros now. So let's move on and switch rows. To switch rows, to move the -1 up, we're gonna have it on top. Now I don't need a -1, I need a +1, so I'll multiply the first row by -1. Once you do that, I end up with 1, 6 plus I, 0, 0, 0, 0. To write the equation and solve for it, we get the vector V equals R multiplied by minus 6 plus I and 1. So if you call x2 a free variable R, this right here reads as 1 x1 plus 6 plus I times R. You move it to the other side, so x1 equals minus, that's the minus x plus I. You could distribute the minus. I'll show that at the end as a comment. You don't have to, but that's an option. Here's more if you need steps. Alright. Okay, now lambda 2 equals 3 minus I. It's usually the conjugate if you are dealing with complex numbers. Was mentioned earlier right here. Now what did I mention earlier? If lambda 1 gives you V1, which is not fully clear here because we have complex numbers, V2 that corresponds to lambda 2 will be the conjugate of this. That's what I'm gonna show. The eigenvectors in this case are those vectors in C2 complex numbers of the form V2 equals V1 conjugate. So what is V2? S times minus 6 minus I and 1. 1 does not change. The plus I inside is now minus I. If that's a little bit confusing, you could distribute here the minus sign, and you will see that in the coming note. I don't want to just read it. I'll show it to you. The eigenvectors corresponding to the different eigenvalues are linearly independent vectors in C2. You don't have to test it. It's a fact. Just keep that in mind. Here's a summary to what I was trying to say to you. So the matrix A was given to me, and we tried to solve with lambda inside as the determinant of A minus lambda I. We came up with lambda 1 equals 3 plus I, which means lambda 2 is a conjugate, which is 3 minus I. Lambda 1 gave me V1. You notice that I took the minus inside, I distributed the minus side. So once you have this, you're almost done. You just need to write the answer for lambda 2 and V2. Lambda 2 is the conjugate and V2 is the conjugate. Minus 6 minus I minus 6 plus I, and that should do it. for this problem. We're almost done. So we kind of covered a few ideas. Before I go over it, let's just close this problem with defective non-defective concept. So the matrix is a 2 by 2. N is 2. We have two vectors, v1, v2. So what we say is A is non-defective. So what I covered here in this section, the eigenvalue lambda, the eigenvector v, and I showed you that they communicate in such a way that AV equals lambda v. Then we solved a system that refers to AV minus lambda I times v equals 0, which comes from A v equals lambda v, and we use the concept of the determinant, set it equal to 0, to look for non-trivial solutions. First example was 2 lambdas, gave you 2 distinct vectors, non-defective. Second example was repeated lambda. Third example was complex lambdas. So what is lambda, what is v? AV equals lambda v. Example 1 was 2 distinct lambdas. They gave you 2 distinct vectors. Example number 2 was repeated lambda. Could happen. It doesn't mean like those examples, you can't take them as facts. Like when it's repeated lambda, it's gonna fall short and it's gonna be defective. No, problems are different cases, so you can't use that as a fact. Like if it's repeated, it's gonna be defective. All what I'm trying to say is we practice distinct and repeated lambdas, and the final example was this one, which is complex lambdas and complex vectors that corresponds to it. That should do it. Thank you for watching. I hope that it was helpful. Hit the like button if you do like it. Subscribe, comment below, and if you like this video, hit the bell icon to be notified when I upload new ones. I'm planning to upload 7.2 soon, and within a week 7.3 and 7.4. Until next time, peace. JaberTime.